I'm standing here with Sepp Hochreiter. Sepp, welcome to our LinkedIn live stream.
Hello. Good evening, everybody.
Good evening, good morning. It's very early in the morning for us. We woke up at 5 to organize this LinkedIn live session. We want to talk a little bit about NeurIPS, about the main topics, about xLSTM for sure. And you presented in your keynote 2 days ago, I think. There was a message. The bitter lesson is over for when it comes to AI. What does that mean, Sepp? The bitter lesson is over.
First of all, I have to explain what I mean with a bitter lesson.
Yeah.
The bitter lesson was a statement of Rich Sutton
2019 or something, yeah.
About 2019. And this statement says progress in machine learning was only achieved by scaling up some models.
We saw that in the last years, right?
We saw this in the last year. Scaling up means the models became larger, more parameters, more data was used to train the models, and more compute was used to train the models. Meaning making everything bigger and larger was the key to success.
Mm-hmm.
And inventing new methods or having good ideas or innovation did not bring so much performance gain.
So the human was not in focus.
The human was in focus, but only for scaling it up. But so human ideas, the cool ideas of the machine learner were not important at this point. But nowadays, with the lesson is over because we enter a new phase. The phase is industrial AI. And for industrial AI, we need these new ideas. We need innovation. We need this.
Because we have specific problems, right, in the industry or in different domains, right? When it comes to safety, when it comes to cybersecurity, when it comes to what else?
Yeah, exactly. Especially something like robustness.
Robustness.
If we use these methods in a production system, the production process should not stall, should not
24/7, right?
and therefore you have specific constraints. Safety, if the AI works with humans, should not hurt humans. And there are many constraints in industry. There are so many requirements if you want to bring something into industrial processes. And here we need new ideas, we need new techniques, new models. And perhaps the models have to become smaller. They have to become more trustworthy. All this stuff will come. And therefore we need again research. We need again some ideas from the community.
But we don't need basic research. Basic research we did the last 50 years, right?
But it could be basic research built on top of this scaled up things. Perhaps you have to have a new idea how to do something. But it's also engineering, how to make it work, how to connect it to a production process or in an embedded system to robots, to drones, to cars, whatever.
You mentioned now smaller models, reliable models, robust models, models on the edge, embedded models. That's the part when an xLSTM comes in, right? You presented a 7B large language model based on xLSTM, but your main focus is not language, or am I wrong?
No, the main focus is not language. We showed that we are good at language. We want to
That we can scale.
That we can scale, and we showed that we have a powerful model, we have a powerful technique, and these days we show it at language. But our goal is to apply it to different domains, especially in domains where inference speed is important. Inference speed means after training, if you apply it, how fast is it? And with xLSTM, we are much faster than the transformer technology. We are much more energy efficient.
That's point, right? Yeah.
We need less compute, and we did it in a shorter time. And this is very, very important, for example, in robotics, in
Drones,
in embedded system like in drones, in self-driving cars where you have also a smaller system, or in automated production systems,
PLCs,
where you put your system, your AI, in the engine, in the machine you use in production. And here you need two things. You have to be small, and your xLSTM XLS, it has a smaller memory, and you have to be fast. And xLSTM is much faster. It's linear compared to quadratic of the transformer technology. Therefore, it's ideally designed for industrial applications.
And when it comes to transformer, you mentioned it's linear. Can you go a little bit more in details? What is special, maybe to compare to transformers, but also to compare to the, let's call it the traditional LSTM?
Now, first steps to transformers. A transformer, if they produce a new item, a new word, or a new data point, they have to look back at all previous data points.
Yes.
And if we add every data point, you have to look back at every previous data point. This comes up to a quadratic in complexity. LSTM and also xLSTM, they have a memory. If you produce a new data item, you only look at the memory. It's a constant memory. Has always the same. All the information from the past is in your memory, and therefore you're so fast because you only interact with the memory, with the stuff you stored, or not with every item. And perhaps you stored very few things, and then you're super fast. xLSTM, compared to the original LSTM, has
Because there were some limitations, right, when it comes to LSTM.
exactly. Our idea was to look at the old LSTM and see whether we can scale it up. Can we make it big? Can we make it performant like transformers? And there we identified three limitations. First limitation was that the original LSTM could not revise storage decision. If you stored something, you can say, oh no, something more important comes. And this was solved by exponential gating. This exponential gating, you can upweigh as a current item you want to store and downweigh as an item you stored earlier. Therefore, you can be adaptive to the new input. So old LSTM could not do it. Exponential gating, number one. Number two was matrix memory. So old LSTM has only a number as a memory, and now we use a matrix as memory. So matrix is actually a Hopfield network. A Hopfield network,
Very famous in these days.
right? Exactly. If you think about the Nobel Prize, it's the classical Hopfield network where John got the Nobel Prize, but equipped with LSTM things, equipped with input gate, forget gate, and output gate. It's a combination, a marriage between the Hopfield network, the Hopfield memory, and LSTM. The LSTM cell is now Hopfield memory. And therefore we have much more memory power. We can store much more information.
You wrote a paper, Hopfield is all you need, right?
Yes, Hopfield is all you need. This is Hopfield network is all you need. This was a paper, making the connection between attentions and traditional attention and modern Hopfield networks. Okay. But we went back to classical Hopfield networks because they're much more efficient, they're linear. And we said we need as inference efficiency. Therefore, we resort to this classical Hopfield network, which is much faster because it's linear.
The third limitation?
The third limitation was transformers were parallelizable, but LSTM not. LSTM was slower in training because you could not parallelize training.
Sure.
And by modifying the hidden connections, we could parallelize xLSTM. xLSTM is now as fast as transformer,
And you're fastest in flash attention, right?
yeah, and that's exactly. It's not even as fast as transformer. We could figure out to make it faster. We are fastest than flash attention because what we now can do with this recurrent idea is chunks of flash attention. We have a small chunk of flash attention, do the recurrence, another small chunk of flash attention. And if we design the chunks in the right way, we are faster than doing a flash attention over the whole context. If we have chunks of the context as flash attention, therefore we are faster than flash attention, which means we are the fastest method on the market. We are the most energy efficient method on the market, and it's both for training we are faster and energy efficient, and for inference. Inference was our target. Inference was more important. Inference is if the user uses it and you save energy, but it turned out that we also in training get more energy.
This is new, right? When you first published your paper, xLSTM, I think in spring this year, training was not sure if you are faster, right?
We thought in training we would be slower, yeah, but with this idea of these chunks of flash attentions, it turned out that we can be faster because we can use the GPU as a graphic processing unit, the chips it's running on. We can use it more efficiently. We can design the chunks of flash attention exactly fitted to the GPU.
And that's important, right? You can customize it on the chip of the customer, right?
Exactly. We can customize on the chip in terms of speeds, but also in terms of memory. We can fix the memory. If we know we have this device or that device, we know there's this memory, and we can fix the memory and design everything around this fixed memory size. And that's a huge, huge advantage over other technologies.
Absolutely. And there's also more, right? It's a vision xLSTM, a bio xLSTM. Can you go a little bit more in detail when it comes to the vision xLSTM?
The vision xLSTM is a vision transformer, which became very famous. But instead of transformer, now using an xLSTM. Vision transformer, you have these patches in the image, and you have a sequence of these patches. You go over the sequence of these patches and then classify what's in the image or whatever you do in vision. And now we use the vision transformer idea, but replace the transformer by an xLSTM. And it turns out that the xLSTM is not only faster, yes, it's faster, but it's also better in performance. For example, in semantic segmentation, it's better in semantic segmentation, but also in different other disciplines.
And this is important for medical applications, right?
It's important for medical
and industrial applications too.
Yes, but vision has many applications. It could be medical, it could be industrial application. It's like quality control. If you have a piece, make an image, I want to see if the quality is there. But making picture and the thing what's on it. Sure. It's always logistic. It has many application industrial.
Computer vision or machine vision was the biggest topic, right, at the NeurIPS this year.
That's true. Computer vision is a big topic, especially with these diffusion models. They are very prominent in the conference. The second most prominent topic was language. Yeah, these large language models and stuff.
But let's go on with a bio xLSTM. I'm also interested in this bio xLSTM.
Bio xLSTM is
within so Günther.
Yeah. Yes. It was. So research was done by the group of Günther Klambauer at the JKU and the Johannes Kepler University in Linz, and they used the xLSTM for scanning biological sequences, and this could be DNA, proteins, or it could be small molecules, chemicals, which may serve as a medication, which may serve as medicine. And it turned out they were already work with transformers, with state space models, and it turned out xLSTM, which is by far better than others. In one of the experiments where xLSTM was applied to proteins, you have homologous proteins, and you want to see if a new protein belongs to the same family or even generate a new protein. xLSTM was much better. But it turned out the other two methods, the state space models and transformer, can only use context lengths of 36,000, and xLSTM improved up to context lengths 260,000. 260,000 context lengths. It's unbelievable for transformer or for other methods. And it's not only that it can cope with it, it improved, xLSTM improved with more context lengths, and this is astonishing.
Yeah, absolutely. Let's talk a little bit about NeurIPS. What was your main? What is your opinion on NeurIPS today? What is What was the main topic? What were the main discussions at the conference?
It's quite diverse. I don't see a clear topic. I couldn't identify. I think it's so many things. Okay, so there were many vision applications, many language applications. Large language models are still very, very prominent, where you try to analyze the large language models. What can they do? What can they not do? When do they hallucinate? To use them for different applications like planning or whatever. There were a lot of papers or many papers in this area, but I don't see some clear path. It was still that these big models, both in vision and in language, where you have these big models, are applied now to different domains and different tasks, to different applications.
And data was also a very big prominent topic again, right?
Yeah.
I thought this topic is over, but Fei Li said everything depends on data. I think when you train bigger and bigger and bigger model, you need more data, more data, more data.
But we don't have more data.
Yeah, exactly.
In language, also in vision, because you scrapped the whole internet and used all the images which some persons put on the internet, and you have the same problem. This text, we already used all text. We run out of data. We run out of data for images. We run out of data for language. And therefore,
Open available data.
yes, open available. But you can start to, to write new text.
Yeah, sure.
But it's a very slow process. Absolutely. And it takes long. You can start to take pictures.
Yeah.
But we also a very slow process. Therefore, it's saturating. And also, using data which is machine produced does not work, because it's using the old information and only transforming the old information, and therefore you're focusing on more and more the same things.
Yeah.
It has a disadvantage. But we know data was important. This was the scaling up phase. It was the major thing in the scaling up phase. Can we get more data? Use larger models with more data. This was the scaling up phase. But now we will enter the industrial phase, where the data is more specific. It's data from one time series, for example, time series, but also images. It's exactly the images of this camera of this company, or computer languages. Perhaps the computer languages, the code used in this specific company in this specific way. And now we get more specific data, particular data for a particular task, and not this huge general data. This is over, I guess.
Last question, Sepp. xLSTM became very famous in the industrial sector when it comes to time series. What about time series and xLSTM? Is there also a connection?
Yeah, of course. xLSTM is a better version of LSTM. Everywhere where LSTM works, I would guess xLSTM works better, sometimes much better. And there were publications out, there were several publications that applied it to xLSTM, they applied xLSTM, the new LSTM, to time series. It's a new state of the art, they improved. And it was one publication after the other. They changed the old LSTM with the new xLSTM and got better results.
Okay.
And this trend stays, and I'm convinced if you replace LSTM by xLSTM, you get better results. I'm sure of that.
Sepp, thanks a lot. Thanks you everybody for joining our LinkedIn live stream. We are going now to have a little bit of breakfast.
Yes.
If you have any questions, write us an email, write us a direct message. Looking forward to see you all in Linz. You are invited. Try out xLSTM. It's open source, right?
It's open source. Everybody can use it. Everybody can build a 7B or larger models if you have enough data. Everybody can use it. It's completely open source, completely free. The model, the training code, and the inference code.
Everything, right?
Yes, that's the model.
Yeah.
So the model, the training and the inference code, everything is open, and nothing is hidden behind our walls.
And we are looking forward to see your results. Share it, give us a call, give us an email, a message, and we are looking forward. Sepp, it was a pleasure. Thank you very much. And now for breakfast.
Yeah, sure. Have a nice day.
Bye-bye.